Hello and welcome to this video on graphing radical functions. Today we'll be focusing on the graph of a square root function and its various transformations, along with identifying the domain and range of all of those functions as well. Before we get into the graphs, we're going to talk about something called principal roots. So when we take a square root, like the square root of 9, for instance, we know based on past experience that the square root of 9 is equal to 3. We know that because 3 times itself, it equals 9. And that is something we are all familiar with. Based on our previous chapters with dealing with quadratics and x squareds, you might be thinking to yourself, well, I actually know that there are two answers. So I could say that square root of 9 could equal to negative 3 because negative 3 times negative 3 is also equal to 9. And you would be right, but in this case, when we talk about the square root of 9, we're talking about the principal root. So this right here, the first line up here, is referring to the principal root. The square root of 9 is implied as being positive. If we wanted in the second part to talk about negative 3, you would need to mention that that's the negative square root of 9 is talking about the negative version and the negative 3. You could also write all of this as something like plus or minus the square root of 9, and that would be equal to plus or minus 3. When we get to the graphing portion of this, it will become more apparent why this is very necessary, and I will make sure to mention it as we get there. But now we are ready to move on to some notes about graphing square roots in general. We have the parent function graphed up here at the top, and we could even make a quick table of values for our y equals the square root of x graph over there at the top of the slide. So we can see that it's starting out at 0, 0, and then we are going to the point 1, 1. Obviously, the square root of x and square root of 1 is going to equal 1. And then you would have the square root of 4 is 2. And then if you want to go past what our graph shows, you might say that the x equals 9 would give us 3, and x equaling 16 would then give us 4. And that is how you would plot the graph if you're trying to graph the parent function, or the original function without any transformations having happened to it yet. So now if we were to include all these same x's and they could give us two different answers, like if we added it on a whole nother slide here, our column, like if we had a y2 column over here, well, we would have 0 is fine, but if we square root of 1, if we allowed it to equal negative 1, square root of 4 we allowed to equal negative 2, and then negative 3, and then negative 4. Well, that would mean that we would have a whole different part of our graph here, and it would make kind of a sideways parabola. You might be thinking to yourself, well, I know that's not a function, and you'd be right. It fails the vertical line test. We can draw a line straight through it. There are two different y values for one x value. And when you're talking about functions, that is not allowed, and we cannot have that happen. So when you're talking about square roots, in order to make sure that we're talking about a true function, to have an input only is going to one output, we need to make sure we're only talking about the positive version of our square roots. If we're ever talking about negatives, we'll have, like we saw in the last slide, a negative square root implied very obviously in that case. Now that we've cleared that up, let's look back at our notes on this slide now that we get rid of our non-function parts of this. So if we look at our bullet points here, we're identifying the starting point h comma k from the equation. H will be usually the opposite and k stays the same. And basically that's going to kind of work similarly to vertex form for a parabola quadratic. And here we have the 0, 0 point where it's starting and kind of going up from there. And the A value, kind of similar again to vertex form, you will know that that's how much it's kind of going up and going to the right one and then going up by that amount. It's kind of its initial slope of this square root function. Contrary to quadratics, the square root functions are going to increase quickly at first and then start to level out as you get to bigger and bigger numbers. As you can see, x is growing in our table at a much faster rate than our y values are growing at. We will do a few examples here of graphing square root functions and outlining what we are looking for in them. So the first thing I would want to do is figure out my starting point. So it's going to be the opposite of my inside number and the same as my outside number. And so I'm going to plot -4, 4, both there and on my graph. So I have my point plotted, and my A value in this particular problem is just a 1. So value of A is 1. And that means that I'm going to have my first point be over 1 and up 1. And I can kind of draw my graph through those points and get a rough picture of what that square root graph would look like. So now kind of to start things off, if you are talking about domain and range, this is kind of easier to do visually as opposed to algebraically. So we'll kind of do that at first and then kind of think about it algebraically in our later equations. So we know we have a solid dot here at the beginning of the graph, and it's going up and to the right. So our domain first, we could write it in two ways. We could say that x is going to be greater than or equal to -4. Or if we wanted to write it in interval notation, we could write it as -4, comma, positive. Let's try that again. -4, comma, positive infinity, like so. And then if we look at our range is going to start at 4 for the y-axis and then go upwards. So our y is going to be greater than or equal to +4, or from 4 to positive infinity. Now, if you kind of look at what we have in the equation here, the +4 in the end ended up being what our range was, and the opposite of what was inside ended up being what our domain was. And that's not an accident, and we'll kind of see that happening in future examples. But generally, that's really all you have to do when it comes to graphing square roots in this first problem. Problem number 2 is a little bit more advanced. So we have our starting point in this one is going to be 1, 2 based on our h and k. So 1, 2 is going to be plotted right there. And then our a value is 3. So because we have a positive square root function and no other reflections happening, we're going to go over 1 and then up 3 spaces. And then we can draw our square root function, kind of a rough sketch, something like that. Now, when we are talking about square root functions, thinking about this algebraically to tackle domain and range, there really isn't going to be a lot more going on with the range other than looking at what this number is in the end, the +2. So the range is just going to kind of basically be that 2. And then you have to look at, well, is it going up or down from 2? In this case, it is going up from 2. So we would say that y is greater than or equal to 2. Or we could say that it is going to be starting at 2 and going to positive infinity. The focus would be definitely understanding the inequality part. Now we can see what's under the square root is x minus 1. So if we had x minus 1, we would basically say, well, we need what x minus 1 is equal to be at least 0. We can't be putting negatives into a square root, but that's going to create imaginary numbers or lateral numbers, or however you want to refer to it, and we don't want that to be causing an issue in our problem. To wrap this up with our domain, we basically if we need x minus 1 to be at least 0, we can basically write it as an inequality. So we just write x minus 1, whatever that part under the square root needs to be at least 0 to make our number a real answer. So if we just added 1 to both sides, we would see that x has to be greater than or equal to 1, which we see in our graph is accurate. So we would just write that as x is greater than or equal to 1, or from 1 to infinity if you wanted to write it as interval notation. And that wraps up example number 2 for graphing. Example number 3, we have some similar things happening with h and k, but now we have a -2, which is going to throw kind of a wrench into our work here. So first off, we have 3, -5 as our starting point, opposite of the -3, same as the -5. So 3, -5, 1, 2, 3, 4, 5 would be that point in blue right there. And then if we have a -2 right here, well, that means that -2 is going to first mean it's going to reflect upside down, reflect downwards. And it's also like the 3 before is going to get dilated by 2 and go down twice as fast as it would be otherwise. So we would be going over 1 and then down 2 spaces. And so our general picture of our square root function is going to be something like that one right there. And that is because our value of a is -2. And then our domain, we'll think about the -2 is not really going to affect because it's the dilation. We're still starting at the same place. So if we knew that x minus 3 had to be at least 0, well, that means we know that x is going to be at least 3. And you can see that on the graph that our domain is starting at 3. So it's definitely going to be at least 3, or x is greater than or equal to 3. And our range, as you can see in our graph, and our number on the end is -5. So y is going to be, in this case, less than or equal to -5 because we have an upside down square root function. And that's a pretty common mistake is with range. Remember, you want to think of it as being, are we going down or up from the original starting point? And that's different than how domain works. We also want to write down our intervals, not something we really need to focus a lot on, but when you have the less than signs right there, well, that means we can basically start at -infinity, which is a little confusing for some, and then it's going to end at -5 if we're going bottom comma top of our function, basically. And then our domain is the same as before, from 3 to positive infinity. So we have, in general, the a values. The a is just like before, it is causing a dilation. If it was a 2, it's going up at twice the rate as a normal square root function. And if a is negative, we can say that it is a reflection. For h, we know that that is going to be a horizontal translation, or translating left and right. And I'll just abbreviate that. Translate left or right. And then for k, that's also a translation. And in this case, it is moving up or down. And that's kind of some straightforward, simple notes on that. And lastly, we want to think about if we start out with our parent function and we have certain transformations, what would we write as our equation? So for the first one, if we're starting out with square root of x, we're going 3 down and 8 right. That would mean that we have no a value in the front, so that's staying as a 1. The 8 units right means we're going to have the opposite and be x minus 8. And the 3 down would mean we have a minus 3 on the end. And we have a scale factor of 5, or a dilation by 5. We are reflecting it upside down and then going 9 up. So that equation would end up being equal to a reflection and a factor of 5 would mean we have a negative 5 in front. We have no translation left and right, so we would just have a square root of x. And then 9 up would be a plus 9 on the end, and that would be our equation there. Some summary points here at the end of our video about square root functions. Remember, we're going to be kind of graphing kind of sideways half parabolas. We can't graph a full sideways parabola because we don't want to have it be kind of failing that vertical line test. We need to have it be a function. We don't want to have one input giving us two different outputs. Second, we talked about the parent function of square root of x, and that a square root is implying the positive principal root. So we're going to graph the square root of x as being kind of all of those positive square roots as the parent function. The transformations we saw with quadratics apply here too. We can have it reflecting up and down. We can have it dilated smaller or larger, or steeper or flatter, however you want to put it vocabulary wise. It can also be translated left, right, up, and down. And we practice graphing along with going with domain and range. Key point that it's much easier to figure out the domain and range if you have that pulled up on your calculator or on desmos.com/graphing, whichever your preference is fine. And then we graph them, including the domain and ranges, like I said. And now we are looking at making equations from the transformations themselves and getting an equation from that. And then you could potentially then graph that function to see how it changed from the original. And that covers all you need to know about graphing square root functions. Thank you for watching.